Well, thank you for coming and uh, I always forget your name. I'm asking about tech support. Uh, Mason. Yeah, thank you much for continuing to support. It is important and for investing your time for um opening your ears to information that maybe not needed. Okay, so you get most universal education on campus. Yep. Okay, okay. So um, I am going to switch to the slides. So if there will be soon, when there will be slides, please distract me by voice. Tell me if you want me to stop or to um, go over something, or if there are questions. So when going to slides, I will be um, seeing only the slides and will not see your faces. So who we are and what are we doing? So it is computational chemistry class. The goal is to predict properties of materials and molecules with specific software, and among properties we mean stability of a molecule, mechanical, electronic, optical properties such as, for example, conductivity or absorbing or not absorbing light at certain frequency. And we did started with several chapters going from atomistic models to Born-Oppenheimer separation. Then we discussed the algorithm to improve the geometry to more realistic arrangement. And then there was a chapter on Hartree-Fock theory, which shows how to reduce multi-electron interaction into mean field concept that is being solved through self-consistent field approach. When linear multi-electron problem is reduced to non-linear single electron problem, and non-linear problems are solved. One of the way to solve them is iteratively rather than diagonalizing matrix at once. Right now, we did started the chapter on density functional theory, which is maybe it is not most precise, but it is best cost-efficient method, which is very much appropriate for large materials. I just want to bring up my assistant.
It's me too.
To the best of my what? It is he or she. Originally, he was he. But we got him when he already was not he. and he's for his species he's older than most of us, so he's like 13 years old, which is
13.
Yeah. So density functional theory, which uses a very original way of solving for multi-electron problem. we didn't.
Dr. Dimitri, can I interrupt?
Oh yes,
A
please.
bit? I cannot see anything. I don't know why.
You cannot see anything.
Yeah.
Interesting.
Allow your camera from the desktop, from the browser.
What do I do?
Allow the access of your camera.
Allow the access. Okay.
Sorry.
That's okay. Mahek, were you able to?
See.
Huh?
I cannot. I can see only myself. I cannot see anything else.
Interesting.
Can you see me?
No.
Um,
You may can disconnect and connect again. Maybe it works.
Okay, let me try that again. Okay, Dr. Dimitri, you continue. I'll try to join.
yes,
again.
yes. And just in case something happens, I'm trying to record it, so there will be recordings. And even if I fail to record now, there will be similar lecture from the previous year to share. So do not
Okay, okay.
do not worry.
Thank you.
Gwendoline is checking if we can hear her, and I don't think we can. There is a chat on the side panel, and while we are watching faces of each other, I can also type something and answer. But when I will go to the slides, they will take all my space. So please, later in a couple of minutes, if you need to interrupt me, please do it by voice.
Now I can see it.
Aha, excellent, excellent. And now I see more boxes with disabled cameras. So where did I stop? Okay, density functional theory. The Hartree-Fock theory used idea of self-consistent mean field, but it still was using everything about the concept of Slater determinant for antisymmetry of wave function and additional part in the electron-electron interactions, the so-called exchange. The density functional theory is different in several aspects. Of course, it is a good descendant of Hartree-Fock, and it uses some concept from there. But in addition, there are several tricks that help to slightly, somewhat increase precision and substantially speed up the calculation. The main idea of density functional theory is that one uses the concept of electron density instead of multi-electron wave function, instead of wave function. So we go from wave function to density. The goal is the same, to get total energy. And before we move towards practical aspects of the calculations, how the total energy is computed, and also from our last practical lab, you already got an idea that density functional theory also uses concepts of orbitals, molecular orbitals, that are being occupied by electrons. So there are some similarities. But before we get to this practical algorithm, we were focusing on the theorems that prove that density functional theory is legitimate. this focus on theorems will not help to solve any practical problems, but it will prepare you to address possible criticism of your colleagues if you go further into the research and getting some useful results with density function theory. So there are two theorems we focused on. First of them that tells that density determines external potential. If you know density, one can find external potential and total energy, and if there is one density, there will be one total energy. We were proving the theorem from ad absurdum method. We got that some crazy inequality pops up if we do not believe into this theorem. And I'll probably show I may show a couple of slides on the theorem again. And there is a second theorem stressing that one is there is stressing again that there is one and only one total energy. Today we need to focus on the way how to remove electron interaction from consideration. There will be completely crazy material in what we are going to cover today. In some sense, we can call this lecture "How to Get Nobel Prize." So there will the density functional theory is really much simpler than most of the theories and experimental setups, but it has very non-standard direction of logic, and you will see example of this out-of-box logic today. In summary, very briefly, the density functional theory assumes a parallel universe. A parallel universe where electrons do not interact to each other, same as in Thomas Fermi theory. And then there is this theory establishes a bridge between our real university, not university, universe, real world, our real world, and this fiction, abstract world. So in our world, electrons interact to each other. In fictitious world, electrons do not interact. But one can design this fictitious world in a such way that there are molecules similar to our real world, and they will have the same total energy. So if this step is possible, then we will do all calculations in modeling fictitious world, but get the answer that will be valid for our world. So on one hand, today we are considering how to get Nobel Prize. On other hand, we are considering science fiction, how to go into parallel world where electrons do not interact to each other. And things that we are doing today are important preliminary steps towards learning the algorithm, how density functional theory works. A comment on administrative side. I did notice that the last homework was a little challenge. There were only two, like 5 minutes before the lecture, there were only two classmates who submitted the homework, which means, and we do not want to spoil any grades, so I think it will be prudent just to extend the deadline a little bit. What I do not want to do is to cancel the next homework. So in about a week, we will complete 2 homeworks by Tuesday. At least we'll try. And we will tomorrow, the Wednesday evening lab will be a biggest challenge for me in 10 years, and maybe for you the biggest challenge in the last 2 months, because we will try to do the lab through this online connection. I will think about it, and we'll find a way to do it. For example, if someone has difficulties that need my help, I can go into the directory of the person who needs help and project his or her directory on the screen for everyone and type some commands there, and then do it one by one for everyone. Something like that. We'll discuss it tomorrow. So the goals that I intend to complete for sure by the end of today's meeting is to introduce this auxiliary world and transition from our world to auxiliary world. If time allows, if you do have energy, I will show the way how to connect orbitals and total density, which is quite simple. It may take like 5 or 10 minutes, but it is slightly different subject. And if you get tired, we will postpone it for Thursday. We'll see how it goes. So I'm going to show slides and ask if you do see them. Please say louder, because when I'm showing slides, I do not see anyone. If you do not see slides, please tell me. I can fix it.
I cannot see the slides.
I cannot see them too.
Okay, excellent, thank you.
I can see them now.
Yes,
Okay.
I can see them.
Yes, I was seeing them for a second, and they just. Oh, okay. Yeah. Okay, I believe you are seeing slides now.
Yes.
Okay. So.
You're developing this painting.
Pardon?
That's it.
I know that slides appear a little bit later than I click the button. And very soon, this is a slide showing the votes of the previous year attendees, but we will fill this table very soon to have a session on. It's 19, not 20. Also, there are several slides that I probably will postpone to next meeting. It is just way to waste time for me, and later it will be useful. We will need to select projects for the last month, and when soon I will start reviewing possible options, like interfaces for photovoltaics, photocatalytic interfaces, some bio-related things, metal clusters, and here is the photo. Sorry, I went out of slides. Yes, here is the photograph and biography of Walter Kohn, who departed from us about 2 years ago, but he lived a long life and he got the Nobel Prize for density functional theory. So it's his ideas that we are going to cover today. Original density functional theory that follows out from theorem is so-called orbital free DFT, where energy is extracted completely from density. But later on, for practical purposes, one uses concept of orbitals because they are really helpful to find kinetic energy. And the first theorem that we went in very fine details was that if one knows the density, then out of density one can find external potential, wave function, and Hamiltonian that allows to find any observable, including total energy. The second theorem is that if we take the wrong density, then the total energy and plug it into this functional, that then total energy will be bigger than the ideal total energy. So the correct ground state density determines only one total energy, and it is a minimum total energy. If the density is wrong, the energy will be bigger. If density is correct, it is at minimum. So we do need to move towards practical steps for implementing density functional theory, and it is possible to live without orbitals. There are some practically available implementations of density functional theory that compute kinetic energy out of density only, but we will be using auxiliary orbitals, and it is just a way to make it numerically efficient. So a little bit of definitions. So what I'm going to tell now is not a class material. It is a background that will help us to express ideas behind this theory. In this slide, I'm going to focus on the interaction between electrons and nuclei, which we called external potential, and that includes Coulomb attraction. Should be minus sign in front. Coulomb attraction between electrons and nuclei. And on the language of density functional theory, it is a external potential that contributed by interaction with ions which are external, which are not citizens of state of electrons. And if one knows the interaction between electrons and nuclei in form of this potential, multiplies it by charge density of all electrons and integrates over space, it must provide the energy of interaction between electrons and nuclei. This comes from, this goes along with classical consideration. If you take this expression in the blue circle and add additional summation over all electrons under index lowercase I, then we will scan over all possible pairs between electrons and nuclei. Since we do have continuous density distribution, we replace summation over all electrons into integration over all spaces, all positions in space. So integration between potential and charge density gives the potential energy, the energy of electron-nuclear interaction. Now I am going to remove the integral sign, one thing, and combine together the density and infinitesimal increment in space. Some people put here index 3 showing that it is three-dimensional. So three-dimensional integration. The combination of density times element of space can be interpreted as increment, as a differential of density. So how much more density we will get if we cover a little box in space. How many density comes out from this this small volume. So out of this small volume, we are getting this delta rho density, a little increment of density. If we multiply this increment of density by the value of potential inside this box, we will get the increment of the energy. So how much potential energy we will get, how much contribution of the overall potential energy of interaction between electrons and nuclei. So the next line is repeating of the previous line with this new notations. So density times infinitesimal increment of the density gives infinitesimal increment of the energy of electron-nuclear interaction. I'm going to ask if anyone has objections against this line, or if you agree, or at least if you do not protest against this equation, please say yes. Okay, no one is saying yes. I am going from slides to the window with photographs, and we'll try to discuss. So I do not see much. So it sounds that some of you may have concerns about the equation that I was showing. That if we integrate in space, if not integrate, if you take small volume in space, multiply it by the density of electrons in this space, it will be total number of electrons contributed from this little space, right?
Yes.
Okay. And then if we multiply this density, which means like number of electrons per space, by potential by the, if you take amount of charge in a specific volume by this external potential, which will be just Coulombic fraction 1 over R electronic minus R nuclear. This should give contribution to potential energy of interacting with nuclei, right?
Yes.
Okay, good.
Right.
Okay, now I am encouraged by seeing your positive feedback. So, and this contribution to the total, not total, let's say potential energy of interacting with nuclei can be named with a symbol, with a Greek symbol delta. Probably we can get scared with the word infinitesimal, meaning that the volume is small, density is small, and this contribution to the potential energy of interacting with nucleus is also small. Okay, so we have a fraction. On the left, we have delta of V capital. On the right, we have V lowercase times delta of rho. Good? Okay, now I'm going to bring slides back and continue. So we are going from this pink line. I need to put slides once again. There is some secret button that, oh, brings me back. Okay, so we need to go from the from this pink circled equation to the next line, and in the next line we are dividing both left and right part by this increment of density, delta rho. So ratio of increments for potential energy and increment of density is equal to the external potential. If you agree with this simple step, please say yes.
Yes.
Okay.
Yes.
Okay, thank you, thank you. So you did agree with this, and now let's interpret what we did. You did a really great step. In the introductory calculus, we all define derivatives, which are increment ratio of increment of function to increment of argument. Here, the denominator is not an argument in the sense of basic calculus. It's not a function. It is. It's not an argument. It is not independent variable. It is function. So let me put it. So this delta rho, it is not independent variable, not variable, but function. So what we are considering is very similar to the concept of derivative, but instead of independent variable in the denominator and in the argument here in the numerator, we have a function instead of independent variable. So therefore, this concept is this mathematical construction is referred to as functional derivative. And this is the main concept that made possible practical implementation of density functional theory. So this fun, even if it is not typed anywhere, I need to then write functional derivative. So there is a noticeable chapter in modern math, functional calculus, where one develops theorems and some interesting features of the calculus where argument is function instead of one independent variable. We do not need to go too far. We need just to accept that this concept does exist. And practically, for us, this concept shows how to extract external potential, V lowercase, out of potential energy and charge density. So practical meaning that we see how to extract external potential. So if there is a procedure of functional derivative, then there should be a procedure of functional integration. And V, E, M is integral V delta rho. So it is integral over all possible variations of the density. So it's instead of this integral over space, one is going to integral over density, and then it is called functional integral. We are using complicated words and advanced concepts, but there will be not too many intellectual challenges. It is quite simple procedure. So I'm going to bring in another little concept, another little idea that we didn't focus while considering Hartree-Fock theory. So the total energy is composed of kinetic energy, energy of interacting between electrons and nucleus, and electron-electron interaction. And from Hartree-Fock theory, we do know that electron-electron interaction is composed of positive Coulomb repulsion, negative exchange energy, and in addition, there is a third term in the Coulomb interaction that is being missed in Hartree-Fock theory. This is called correlation, and in a simple way, one can define it as the part of the energy that is not included into Hartree-Fock theory, because it uses only single determinants. The idea behind this correlation is that I'm going to bring interactive discussion once again. So if we do have, let's say, an maybe a 9 of the hydrogen atom that accumulated one more electron. So there is one nucleus and two electrons. Is it possible that these two electrons will sit simultaneously on the same side of the nucleus? Well, everything is possible, but it's very small probability because they experience repulsion. So most likely they will be coming on the different sides of the nucleus. So they will try to occupy all space, and it means that if after we place first electron, the position of second electron will correlate with distribution of the first one. I have seen instructors and lectures where people illustrated in the form of kindergarten game. So one places a chair into the front of class, invites two volunteers, and asks them to run around the chair, and when instructor claps, whoever first sits on the chair. So when chair is occupied, the second one cannot sit there. Means position of these two individuals are correlated. This is a little childish, but this, and it is not direct illustration, but it gives an idea that there is a additional part of electron-electron interaction that is not literally mentioned, literally included into Hartree-Fock. And in the advanced wave function theories, like MP2 configuration interaction couple clusters, they are included explicitly. In density functional theory, they can be included in the a little artificial way. Yes?
Hello.
Hello. Yes, I hear you. Can you speak a little louder?
There is background noise, so can you please tell everyone to mute their mic, and when they need to talk, just unmute.
That's a good idea. I agree with it.
It's too much background noise.
Okay, I muted.
Oh, okay. Now there is no background noise. Thank you. Okay, I'm going back to the slides. So the density of two electrons is only approximately can be reproduced as product of densities of independent electrons. And in some sense, the correlation energy is defined as difference between total density of true multi-electron density and total density generated of products, independent densities of independent variables. And yeah, I think it is sufficient. Now, this slide is including the main idea of today's meeting, and I will repeat it and show it several times in different implementations. So there are only two lines. First line, that we introduce an artificial parameter, and this parameter is degree of our penetration into parallel world. So it's so if lambda equals 0, then it is real world. If lambda equals 1, then it is artificial auxiliary world. What does it mean in a sense of total energy? The electronic part of energy is combined of interaction between nucleus and electron interaction. We are going to assume that summation of these two components is constant in any world, in real, unreal, and any transitional worlds. But we will be continuously changing the contribution of electron-electron interaction. So if lambda equals 0, this contribution from electron-electron interaction will be 1. If lambda equals 1, this contribution will be 0. And we will try to design to update the external potential depending on the value of parameter lambda in a such way that summation of these terms will stay constant independent whether we are in the real or unreal world. I'm going to quickly look if you can just note with your heads if this idea seems okay. I see there is a question. Is there, if anyone wants to protest or ask question, put the microphone on and I will discuss it. No? Okay. So we are accepting the continuous transition between parallel worlds. And here is the same idea. I'm just repeating it. Maybe in slide is a little better typed. So the way how we describe external potential will depend on the parameter lambda in order to keep summation of electron-electron interaction and external potential interaction with nucleus V constant. So mathematically, we can assume that it is possible. And if this is possible, yes?
Dimitri,
yes?
I think the lambda cannot be 0 or 1. It should be in between. If it is 0, then there will be no interaction, electronic interaction. And
exactly. And this is the point. If you allow this situation when electron-electron interaction is 0, you get Nobel Prize. Well, now it is a little too late. This Nobel Prize is already taken. But the idea is that one is moving away from standard way of thinking. So if one logically allows that total energy is the same with or without electron-electron interaction, and our goal is just to find total energy, then why should we bother ourselves to compute electron-electron interaction? Now you see that it sounds crazy, and now you see why many people were not accepting the theory right away and why theorems are needed. Right? So it is a little counterintuitive. But the developers of the theory carefully made all necessary steps to prove that it is possible. I have brought the slides back. If you do not see, speak up, but I hope everyone sees them. So, in this auxiliary world, we can say it is total energy constrained by the value of lambda equals 0. The total energy is composed of kinetic energy and external potential, which is tailored in a such way that it gives the same total energy. Again, what we are covering now is not a practical way to solve problems, but try to make some records or memorize some of these logical steps, because it will be helpful when you need to defend your findings. So what do we do with kinetic energy? We typically find it as second derivative of the orbitals, if they are allowed, and it is just a little reminder that if we plug in the quantum expression for the momentum, which is derivative over the position with some constants, and if you plug it into this p squared over 2m, we are getting the second derivative. So, next, very small logical step. If the total energy is kinetic plus external potential from auxiliary world, then auxiliary world external potential can be expressed as a subtraction of the total energy, which is known once and forever, and kinetic energy, which we will is easy to find, and we will discuss it later, but it is quite standard procedure. I'm going to look on your faces and check if this little subtraction is okay with everyone, right? So auxiliary potential from this outer world is total energy minus kinetic energy. Now, the next step. We already agreed on the concept of the functional derivative. So if we know the external potential, then we can apply the functional derivative and obtain the potential. But now we are able to replace the electron to nuclear interaction, the external potential, with subtraction of total energy and kinetic energy. So the potential can be expressed in terms of total energy as a functional derivative of total energy minus kinetic energy. Does it sound reasonable? So I do not see much protests, but I will repeat once again. The potential energy can be expressed out of the total. The word total, I'm not quite right using it, out of the component of the total energy through the functional derivative. The electron nuclear interaction or external potential, and through this auxiliary world concept and through subtraction of kinetic energy, now we can express the potential as functional derivative of the total energy. Why it is important? Because potential is a characteristic that can be used to describe one electron motions, one electron orbitals. So this potential is really appetizing, really pleasant, really comfortable concept that has been used for many other theories for decades. And if you can go from the potential, which we call this, which we call this uppercase letters, if we can reduce it to the potential that we call this lowercase, it is a really important practical step. So now I'm going to utilization of the step. So since we know this lowercase potential, if we add it together with kinetic energy and apply to the multi-electron wave function, we can find total energy and multi-electron wave functions, which we are not going to do. It's just auxiliary. Now, the kinetic energy, we need to write, the kinetic energy of multi-electron system can be contributed as kinetic energy of first electron plus kinetic energy of the second electron, and so forth. The potential lowercase, it is found once and forever it is the same for all electrons. Therefore, we can partition our multi-electron wave function and multi-electron Hamiltonian onto these little small Hamiltonians, which will include specific potential energy for each electron, a specific kinetic energy of each electron, and just a proportionally equally share the lowercase potential v over all electrons. So if we plug in this little Hamiltonian into unknown wave function for the first electron, it will be one electron Schrödinger equation that is always possible to solve if the potential is known. But since electrons in this auxiliary world are not interacting, the potential for each electron is the same, and this old text I'm going to, the potential for each electron is the same, and the overall multi-electron wave function can be composed as Slater determinant of solutions of this little particular lowercase Schrödinger equations with lowercase Hamiltonian. Again, this is possible because we are doing this manipulation in the world where electrons do not interact. The idea of going into this world where multi-electron wave function is replaced by so many one-electron wave functions which do not have, which are found in the same way, each of them is found in the same way, is contributed by Kohn and his assistant Schramm. So sometimes people, instead of Schrödinger equation or Fock equation, people call it Kohn-Schramm equation. Kohn-Schramm. And if all above is true, then multi-electron wave function is just Slater determinant of this one electron wave functions. So, if this step was possible, if we have composed the many electron wave function and total energy out of one electron wave function and out of potential, there is only one component is missing: how to construct density, total density out of the orbitals. And I think we are out of time. I would suggest that we postpone the part of composing density out of orbitals into the next meeting. But if majority wants me to continue, I can. So let's vote. Who agrees to postpone the remaining part to Thursday? 1, 2. Who votes to continue now? Okay, 2 versus 0. Oh, 2 versus 1. Okay. Raju, your microphone is off.
Yeah, because I have nothing to do. I'm bored.
Okay, let me express. Oh, postpone. Okay, I see. Gwendoline is voting for postpone. I will, just to satisfy your curiosity, I will verbally comment of what is going on and what will be the next step. But we will go over details on Thursday. So I will match who voted to postpone and who voted to do it right away. So without equation, just look at me or just listen to ideas. If we know total energy and if we know density, then we can get lowercase potential, V, right? If we know V, then we can get multi-electron wave function and total energy. But in order to get from the total energy backwards, to close the loop, we are missing density. So if we will include a protocol to compute density out of orbitals into this loop, then we will be able to make a cycle in the same way as we did in the Hartree-Fock theory. We will be able to use total energy and total density to practice functional derivative, find lowercase v, find orbitals, use v to find total energy and density, and then close the loop. And then we will repeat the loop until the total energy will come to convergence in the same way as in mean field concept in Hartree-Fock theory. Make sense? You do not need to say yes right now because I didn't cover everything. It's just a little heads up how are we going to proceed. Okay, I suggest that it will be end of the meeting number 19. I will stay here to answer any questions. And whoever doesn't have questions is welcome to depart in peace. to complete to complete the session.
Dr. Dimitri.
Yes.
So this theory is for gas and solid because we're assuming that no electrons are interacting with each other. Am I right?
Please repeat once again.
We are assuming no two electrons are interacting with each other.
Yes.
So this is for gas, for the gas system or the solid system? Because in solid and the 3 electron of the, if we assume this is a gas, only then it can happen. But for the chemical reaction, there will be electronic interaction.
Okay. Excellent question. And now you all understand why community was resisting to density functional theory. So the pathway, the actual equation for total energy as a function of the density is not known. Theorems do not give this information. It is a practical task for practical researchers. The theorems and the concepts of density functional approximations show the way, how to achieve, how to find total energy of the system in the shortest way. I remember your question. Do not think that I'm trying to deceptive your attention. Now, the assumption of this existence of two parallel worlds is based on the constraint that external potential interaction with nucleus and electron-electron interaction merged together give the same total energy. So if we assume this logical step, then we can design such formula for the functional, that connects total density with total energy, that will include all forms of electron-electron interaction. So we are performing calculations in the world without electron-electron interaction, but we design the formula for total energy in such a way that it includes all electron-electron interaction. Are you a little more comfortable? Raju? Or not yet? Do not hesitate. Do not hesitate. You are not the first. You are not the first who opposes and objects density functional theory. It is very normal that for the first couple of weeks you do not believe in it, or even for first couple of years.
But this is the most common theory. But today we didn't cover the electron interaction for theory.
No,
we just assumed is as a zero.
Right.
Today.
Today.
Okay, nah, that's fine. Okay.
Okay, so
that was my concern. Are we going to eliminate totally electron interaction or not? Okay, I understand now.
Okay, so the total energy will include all electron-electron interactions.
Yes.
And if it's not quite a correct logical way, but the ultimate proof of any theory is agreement with experiment. And density functional theory gives good agreement.
Because in this theory, they find first they find the kinetic energy, then they find the external potential, then they will find the electron interaction with steps.
I will provide a little adjustment to this picture when we meet next time.
Okay. Thank you.
Okay, but I really appreciate this discussion, and it is very relevant. More questions?
So for tomorrow lab session, we will go through the VASP again. Dr.
Oh,
Quinn,
yes,
or?
yes. We will do the VASP for the rest of semester.
Okay, because for me, for doing the homework, to be honest, utilizing VASP is very difficult at this step.
Oh, I agree.
I hope to learn more, or if you can introduce a parallel, I don't know, references, an online course or something like that, or tutorial, if you have any, if you share us, we would appreciate that.
Okay, yeah, I'll try. I have some materials to share.
Yeah, that's fine. Thank you.
Thank you very much for your time.
Okay, thank you for investing your time in the course. I enjoy your company and your curiosity very much.
Okay, thank you. Okay, see you tomorrow.
Okay, yeah.
Thank you.
Thank you.
Thank you. Have a good day.
Thank you. See you tomorrow.
Yeah, see you.
Bye.
Stay healthy.